In this tutorial, we will try out diffusion for path planning. Starting from the green point, the agent should reach the red point avoiding light blue obstacles. Since this method is novel, the path is not perfect. But, as we can see, using this method we can calculate a path which avoids obstacles on the field. The same technique can be used not only for path planning of mobile robots, but also for robotic arm manipulation. So, what are diffusion models? Diffusion models are a class of probabilistic models used primarily in generative modeling tasks, such as image generation, audio synthesis, and other forms of content creation. Diffusion models define a Markov chain of diffusion steps to slowly add random noise to data and then learn to reverse the diffusion process to construct desired data from the noise. Let's see more closely how the model works. The process of adding noise is called forward diffusion process. It generates a sequence where xt is approximately Gaussian noise. At each step, a small amount of Gaussian noise is added using a predefined variance schedule. Here, beta t controls the noise level at step t. Let's see this formula more closely. Xt is the current noisy sample at time t. Left side represents conditional probability. It means the probability that xt happens under the condition of xt-1. Right side represents Gaussian distribution. The middle term in Gaussian distribution formula is the mean of the Gaussian distribution at step t. It specifies how much of the previous sample xt-1 contributes to xt. The right term is the variance. It determines how much random noise is added at this step. Overall, this formula describes how the forward process transitions between previous step and current step by adding noise sampled from a Gaussian distribution. Now let's see reverse diffusion process. This process is also called as denoising. This process reconstructs data from Gaussian noise. Each step in the reverse process is modeled as this. We need to learn a model p theta to approximate these conditional probabilities in order to run the reverse diffusion process. Middle term predicts where the next denoised sample should be, based on the current noise input and time step. The network learns to align this with data structure. The right term controls the uncertainty at each step. In many implementations, the variance is either fixed or parameterized in a simple way. The training objective is based on the variational lower bound on the log likelihood of the data, often simplified into a denoising score matching loss. Now let's see potential-based motion planning. This method aims to find a collision-free trajectory by minimizing potential function. Potential function is defined as a sum of attraction potential and repulsion potential. Repulsion potential has high values near obstacles and low values further away from them. Attraction potential has low values at the end state and high values away from it. By iteratively following the scaled gradient of the potential function, a collision-free trajectory is obtained. As a weakness of this method, if the solution falls into local minima, the motion plan will no longer successfully construct the path. Given a motion plan from start state to end state, a set of obstacles in the environment and trajectory-level potential function, we can define a successful motion plan as described in equation 1. To find the potential function in equation 1, energy-based model across a dataset of solved motion plannings is used. This is because we assume that successful motion plannings have minimal energy. Optimization of energy landscape can be done with several methods. In this tutorial, we will use denoising diffusion training objective. In this objective, energy landscape is trained so that gradient with respect to the energy function can denoise and recover a motion plan across many differing levels of noise corruption. To train the potential, we will use energy-based diffusion training objective. In this potential, the gradient of energy function is trained to denoise noise-corrupted motion plans from the dataset mentioned above. The training is over when we find parameters that minimize this mean square error. In this tutorial, we use Unette as a network that represents the policy. Unette is named for its U-shaped architecture, which consists of two main parts. The key idea is to combine coarse, high-level features with fine, low-level details, which is especially useful for tasks requiring precise localization. The first important feature of the Unette is encoder. Encoder captures the context and reduces spatial dimensions. Encoder consists of convolutional layers and max pooling layers. The second feature is decoder. Decoder reconstructs the output and combines information from earlier layers via skip connections. Another distinctive feature of the Unette is skip connections. Skip connections link each encoder block to its corresponding decoder block. These connections allow the network to preserve spatial details lost in downsampling, enabling the decoder to combine low-level details with high-level contextual features. In diffusion models, Unette serves as the core architecture for predicting the noise to be removed at each step of the reverse process. Unette processes the noisy image through its encoder and decoder, integrating fine details and contextual information to predict the denoised output or noise. Now let's see the program. Please download the program from the Google Drive and extract it to the home directory. As a base project, we used this repository. Thanks for the author for sharing this great work. To run the program, install all the required packages that are written in the requirements text file. Also, there are pre-generated data sets and weights available. The structure of the program used in this tutorial is based on these tutorials. If you want to know how to use PyQt5 with ROS2 and details of path tracking algorithms, please see these tutorials. Here, I am going to explain the difference. First, we need to install the Gazebo transport library. The installation method is explained in this page. Just follow the instructions and execute each line one by one. Because we use Python this time, we should also install the Python package of the Gazebo transport. Now let's see the program. Here, we import Gazebo transport and Gazebo messages. In these lines, we define the Gazebo node and a service to set robot pose. Next, based on the received path, we calculate initial orientation of the robot and send a request to reset robot position. In these lines, we calculate robot rotation velocity. For path tracking, we use a simple peer pursuit algorithm. But there is a difference in calculation method to follow the path. Previously, we used orientation error of the look-ahead direction and actual robot direction to calculate the required steering angle of the front wheels. But since in this tutorial we use an omni-wheel robot which has no steering, we calculate angular rotation velocity of the whole robot. This value is used in this formula to calculate velocity of each wheel. To run the program, first execute the colcan build command. Note that we add the base paths option to build packages only for the specified directory. Then, execute the Path Visualization Simulator Python script. Here we have to specify the configuration file. The program for this tutorial is tested for the case with 3 static obstacles. We can move start and goal points. To calculate a path, click on the Calculate Path button. Then, in another terminal, execute the main launch.py script. After a Gazebo world appears, click the Path Following button. The robot will begin to move.